I think that we can start now. The exam is being graded, so I suppose you're going to have your grade this weekend. That's what I think. Okay. Oh, I forgot the first term. I'll bring it on Friday. Okay. Do you remember that? That was like the second, third lecture. We were talking about the computer, and those were the instructions of that computer. In case you don't recall, the first one in says that you're going to in the numbers in and out 5, 9, or 7. They are related to these devices here. So if I use in with 5, means that we're typing in data, okay, from the keyboard, and it's going into the accumulator. We say out means that anything that we have in the accumulator goes into the screen or printer, depending if I use 9 or 7. Remember that? Okay. And then we have instructions like load what is in memory location 1 into the accumulator, or store what is in the accumulator in memory location 4. Okay. So, and add means add what is in memory location 4 to the content of the accumulator and leave the result in the accumulator. Do you remember it? Yes or no? In any case, you can take a look to this. This is the second lecture. Okay? But I needed to give you an example about paging. Remember that we say that with paging we're going to solve the problem of external fragmentation. That's what we did last day of class. Okay, so let me show you. I'm going to keep this one in case we need it. What is going to happen when we use paging? When we use paging, the program has to be divided into sections that we call pages. And memory, RAM, has to be divided in sections of the same size, which are called frames. And the idea is that those frames are like page holders. We can put a page into a frame in memory. Okay? So imagine that we have a program like this. In 5, can you see that column? Yeah. Okay. Store, and who is store? Yes. Store in memory location, let's say 0. Then we do, let me do something. I'm going to write the same thing. Let me put here memory locations, okay? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so what we're going to do is that I'm going to leave I'm going to start the program right here in 5, store in memory location, let's say 2. Then we do in 5, store in memory location, let's say 3. And then we do load it's in 2, add where it's in 3 several times. And then we do store in 4, and then we do out 9 to see the result, and we do then out 7, and no, you see that? And then we do 16. Okay, so this is a program that we have in memory. In that machine we were working with, we have an instruction format, and the instruction format was opcode. Here we have the address. Okay. Any questions so far? So for paging, we say that we have to divide the program in pieces of the same size that we call pages. Let's assume that each page has 3 instructions. So we're going to have these divisions here. This is page 0, 1, 2, 3, 4, and 5. You might notice that the program doesn't fit exactly to cover all spaces in each page. The last page, remember that we say that we can have internal fragmentation in the last page. So here we have some free space, and this is internal fragmentation, correct? Okay, now, if we would like to work with this program in a machine that works with paging, we have to do some changes. One is the compiler has to translate the program and have to divide the program into pages. The operating system needs to create something that is called the page table. We're going to talk about the page table in a minute. And the page table is a sort of translation mechanism. Here in the program we have what we call logical addresses. And in memory we have physical addresses. Okay. So the good thing about paging is that we can load a page anywhere in memory. Because logically the program goes one instruction after the other. But in memory we can put this page 2 in frame 200, page 3 in page 5, in frame 5, page 4 in frame 1000, anywhere, because we're going to have a mechanism to do the translation. And for that, we're going to use the page table. Okay. So the first thing we need to know is that the format that we're going to use for paging instruction format for paging is different, because with paging we have a 2-dimensional addressing mechanism. First, we point to the page, we find the page, and then inside the page there is an offset. So we move inside the page and we find the instruction or data we're looking for. Yes?
What does it say after instructions?
Format?
Instruction what?
Instruction format for paging.
Oh, format?
Format.
Okay.
That better? Okay. So the instruction format for paging, we have to change the instruction formats to opcode, page, and displacement. Sometimes in the book probably they're going to call it, instead of displacement, offset. Okay? So P stands for page and D stands for displacement. Or offset, which means how we're going to move inside the page. following me so far? Good. I think this is chapter 8. Okay, so the first thing we need to do is to transform this program to the new format, which means that all memory addresses, which are absolute memory addresses, because we say load what is in memory location 2. So that's, we go to memory location 2, the absolute address. We have to change all of them into into the new format. And first we identify the page, and inside the page, the displacement, the offset. Okay, so let's do the translation. With input-output instruction, there is no problem. Here we have, for this one, the translation would be in 5. There is not any difference on it, okay? But for this one, it says store in memory location 2. In what page is memory location 2? 0. This is memory location 2. And starting from the beginning, what is the displacement? 1, get here. 2. Because we point to the beginning of the page, so the offset is 2. Okay?
So you mean we go from 0 to 2?
Pardon me?
So we go from 0 to 2, right?
Now all the pages will go from 0 to 2. This is the absolute address that we have, but now the mechanism, the two-dimensional mechanism says page, and inside the page, starting from 0 in all pages, from 0 to the end of the page, in this case from 0 to 2. Okay, the next instruction, this one, doesn't change because it's an input-output. But this one, it changes. That one will be a store. Where is 3? Page. 1. Displacement.
0.
Okay, we're doing good. For this one, load. What is in 2? So what is the page?
0.
Displacement?
2.
Okay, for this one, add. What is in memory location 3? So we have, we're in page,
1.
displacement, and this one will be the same thing, right? This one, same thing. And this one here, store, what page?
2. 1. 1.
1 or 2?
1.
Displacement?
1. 2. 1.
1.
1, 2, 1, 4.
Page 1.
We're in page 1, we agree. And displacement?
1. 2.
1.
So it's 2 here.
This one.
Why 2? Remember that now all pages are 0, 1, 2. 0, 1, 2. 0, 1, 2. Okay? So it's 1 or 2?
1.
Okay. Out 9. I'm going to change this out 7. I don't like that one. I'm going to change it by jump to So how can we translate this one? Jump to instruction 11.
Page 3.
Page, displacement, and then halt, doesn't have any address of Holly to Harvard. Is that clear? What is the transformation we have done? Okay, we have divided the program into pages, and now we're going to address memory to get to retrieve instruction or to fetch instruction or retrieve data using the new mechanism, which means identify the page, and within the page, you are going to have a displacement or offset. Okay? So now we have the program ready here for running in a paging system. So we need to do this. There is one reason. Well, there are several reasons. But one, you're going to see it in a minute. Now, the CPU is going to have the format operation, page, and displacement. We're showing here only page and displacement, right? So we need to create something called the page table. So let me tell you what is the page table. The page table is a table that has, initially we're going to say 2 entries. In one entry we have the page number. In the other entry we have the frame address. Okay? So the idea is that if I have an instruction that says store 2, 3, or 2, 5, or 2 whatever, the 2, we use it to find what is the entry in the page table. And then when we find that entry, in that entry we're gonna find the frame address, which means a pointer to the memory location where that frame begins. So as we're pointing to the beginning of the frame, which is here, we need then the displacement or offset to move from the beginning of the frame to the right memory location we're looking for. Okay? Is that semi-clear? 1/3? 1/8? Okay. So we're going to be back here. So we have to modify also the hardware. Okay. So where with this program, the program has been divided into pages, right? And now, may I erase this off? It's not beautiful, but it was nice. I'm going to leave this part here. So what we know is that the program is divided into pages. We have a program here. And let's suppose that this program has 0, 1, 2, 3, and 4. And let's assume that this program has 4 instructions per page. But the last page, let's say we have only 2, so there are some internal fragmentation. So we need to create a page table. In the page table, we're going to have 1 entry per page. If the program has 20 pages, we need a table with 20 entries. If the program has 5 pages, then we need a program with 5 entries. A page table with 5 entries. So in this case, how many entries do we have? 1, 2, 4, right? Correct? That's not correct. How many entries? 5. And the page table, we're going to divide it. Later we're going to see, we're going to put more information in. But we're going to divide it in 2 fields. One is the page number. page number, and in the other side, we're going to have the frame address. And then we're going to have memory. And in memory, we can have many frames. Say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so we have this in memory. And then we can load the page anywhere in memory, the pages. So let's say page 0, this is frame 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. We have 13 frames. So the OS says, well, the OS, when we create a process, the OS, in addition to the process control block, we have to create the page table. And we need to have in the process control block a pointer to the beginning of the page table. We'll talk about that later. So when we switch from one process to another, we have to switch from one page table to another. So let's suppose that here we have page 0. So page 0 is in frame 2. What it means is it's not necessarily that it's in frame 2. We're pointing to the beginning of that page. Okay? Page 1, we're going to put it here. In 8, right? Page 2. Is in 4. Page 3, we're going to have it in 6. On page 4, I'm going to put it. So each one of these numbers, what it's telling you is in what frame that page is, but not the number of the frame, is the initial address where the frame begins. Okay? And that's why, when we take a look to this one, you can see that we take the page number, identify the entry for that page, take the frame, and we use the frame points to the beginning, plus the displacement or offset, which is the distance from the beginning of the frame to the place where the instruction data we're looking for is located. All right? Okay. I'm going to erase page number and frame address. Page number, frame. Okay. If we have another program here, let's say we have this program. This is program 1. Let's assume that we have now program 2. This is program 2. And we have here page 0, page 1, and page 2. The same thing, 4 instructions per page and so on. All right, so I don't know why this light today is. Can you see the difference between the two colors? Yes, right?
Yeah.
Okay. So let me redo this very quickly. Program 2 has 3 pages, which are page 0, page 1, and page 2. So we can load, we have to create a page table for this one as well. Page table for program 2. How many entries? 3. Page 0, 1, and 2. And then we can say that page 0 for this program is in location 11. So means that we're pointing to this, the beginning here. Then we can say that the other one is in 1, so we have here page 1. And then we have 2 and 7. Probably we're going to have some fragmentation here as well. Okay, so now we have 2 programs. They are sharing memory, but they are occupying a different set of frames there, right? And then there is no problem with compaction. There is no problem with external fragmentation. Only a little bit of internal fragmentation in the last page of the program. Okay, so now when we create a process, we have to create now with this memory organization the page table for the program. That's something new. All right, so we have this program there. So what is the format that we're using now? The format is the instruction, the opcode. We have the page number and the displacement or offset. So if we have load or store 02, we have to take the 0, or let me give another one, jump 32. So we have to find 3, right? And then it's in frame 6, and then we add the displacement, which is 2. Are you following me so far? Is that clear? Any questions? Little bit there? Or? I'm sorry. Okay, we were talking about this. Okay. Any questions? No? Okay. So if we're going to execute one of these, like add page displacement, store page displacement, then we need the hardware to be modified to understand our new format. So that's why from the CPU, we're going to send what we call the logical address. Logical address is the address within the program. And we have here page and displacement. And in the hardware, in the CPU, we're going to have now another register, which is going to be called the page table pointer. It points to the beginning of the page table. So if we have that point, when we dispatch the process, we gather from the process control block the program counter and copy that into the CPU, right? The stack pointer, and we copy that into the CPU. Now we're going to have the page table pointer, and we copy that into the CPU. Why? Because that register is pointing to the beginning of the page table, which means right here. And when we add to that address the page, it will move, depending on the number of the page, a number of entries down, and then we'll select the appropriate one. So if the page, in this case, let's suppose this is 1, 2, 3, 4. If this is 4, then from the beginning is page number 4. Because the program, from the standpoint of the user, from the standpoint of the programmer, for us, we continue seeing the program one instruction after the other, right? What is different is how the operating system is handling the program that the OS has sparsed out all the pages, okay? So as programmers, we know that we have, after page 0, we have page 1. After page 1, we have page 2. But how they are in memory is the OS who is going to take care of it. Okay? All right. Now, let me tell you why logical addresses are let's say, how we know that we move from one page to another. Let's suppose that in the format we have for pages we have 2 bits, and for addresses, for the displacement, we have 3 bits. Okay, so it means that in page 0, we're going to have 7 addresses: 0, 0, 0, 0, 1, 0, page 0, displacement 0, 0, 0, 1, 0, 0, 0, 1, 1, page 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, 0, 1, 2, 3, 4, 5, 6, 7. If we add 1, we're saying with this format that each page has how many addresses inside the page? How many? With 3 bits, 2 to the 3, 8, right? So in page 0, we have inside to store 8 instructions or 8 data values. That's what we're saying, okay? If we add 1 to this number, what are we going to get? What is the value of 1, 1 plus 1?
0 carry, so it'd be 0, 0, 0.
Sorry?
So what's the value of that added plus 1? Is it gonna be 0?
Yeah.
Carry?
1 plus 1 is 0, carry 1, plus 1 is 0, carry 1, plus 1 is 0, carry 1. What do we get?
What next be? Oh, for the new page.
8, right? Okay. So what it means is that the next address that we have in memory is 01000. We have, and then we continue with 01001, 01010, and so on, up to we get to 01111. So you can see that if we are running instruction here, and the page number changes, we move to the next page. Okay? So we're gonna have 010, 00110, 00111. If we increment the program counter has 01001, but it means for our format, the interpretation we do, the first 2 bits is page, the rest of them is placement. So we move to the next page. Okay? All right. So now, we have to divide the program into pages. We have memory into frames. We need to create a page table as a translation mechanism. And also, we need to modify the hardware in such a way that the instruction format, when we use the instruction format, we have to access the page table, then get a value there, and then we get the displacement and we access memory. The way that we are, let's say, the way we are organizing memory is, this is memory. Part of the memory is going to be divided in frames. Sorry. This is memory. So part of the memory is divided in frames. That is the part where we're going to load programs and data, and we're going to put the pages and so forth. And in the other part of the memory, we don't divide it, okay? So, for instance, we can have here the page table. We can have here the PCB. So we're using the one part of the memory that is divided in frames only for the user program, but that part of the program that is data, stack, and so forth. The structure that the OS handles to keep track of the processes are in another part of memory where we are not dividing that into pages or frames or anything like that. Okay? Are you following me so far? Okay. So it means that where is the page table?
In just memory.
Memory. Yeah. Where are the pages of the program?
In the program itself.
No.
No, in the page table, which is the memory.
No, in the page table there are no pages. The page table has
Frames.
entry points in the frames. So we create a process control block, right? We create a page table for the process, and we have all the instructions and data. So the instruction and data is divided into pages. We load it on this side. The program is here. But these are the OS structures that the OS uses for taking track of the process. But where is the PCB? In memory. Where are the program pages? In memory, in the frame section, in the frames part, let's say. So the program is in memory, the page table is in memory, the PCB is in memory, everything is in memory, correct? So now, if everything is in memory, let me ask you a question here. Usually, when we have an instruction which is low 7, we just access memory and get the value, right? But how now? Where is the page table? In memory. Where are the frames? In memory. And usually, most books, or I think almost every book in OS, they use a similar image like this one. And looks like this is memory, and they don't say where this is. But this is in memory as well. What it means that with this new mechanism to address pages, etc., we have a two-dimensional mechanism. And the problem is that we have to access twice memory to get the same instruction. So that will slow down the running of our program. But we're going to sort out that problem later. So we take the page, we access the page, this page table, which is in memory, one memory access. We get the frame, take the displacement, add it to the frame, and we access memory, the page that we're looking for. 2 memory accesses. Can you see that? That we're doing 2 memory accesses instead of 1. So we have 2 problems with this new memory organization. One of the problems is that we cannot run programs larger than memory size. In this example, the best we can do is to run a program with 13 pages. If the program has more than 13 pages, we cannot run it in this machine. That's problem 1. In addition, now that we are using paging to avoid external fragmentation, now we have to do 2 accesses per instruction cycle to get the instruction or to get the data, which will slow down the running of the program. Okay? So these are the 2 problems that we have to solve in order to use this memory scheme. And we will do it. We will find a way to have just 1 memory accesses in most cases, very few cases 2 memory accesses, and then we will find a way to run programs larger than memory. To run programs larger than memory, we're going to do that with a technique called virtual memory, but we have to introduce some more hardware to do that and some algorithm in the OS. But to avoid the 2 memory accesses, we're going to use a new device in between memory and the CPU. Usually, it's a sort of cache memory, and it is known as TLB, okay? And also is content addressable memory. We're going to see what it is, what it's at in detail, okay? So with that device, which I will explain, I think next class probably, with that device, we can speed up memory accesses, and which means we can avoid a lot of those 2 memory accesses that we need to access any page. Okay. Any questions? Are you following so far? Okay, good. So, may I raise this up? No question on this? Now, you remember that there is a state called new. And then we create the process, and the process goes into a state that we call it ready, right? What does it mean that a process is in the ready state? Well, it means that we have created the process control block, right? And there we have the stack pointer, we have the program counter, we have some other information mode, and now we're going to have the PTP. The PTP is page table pointer. What does it mean? Remember that we have to create a runtime environment, right? And here we have the stack. And here we have the text or the code. Scope, also known as code. We have the data. We have the heap. They grow this way. So the stack pointer points right there. The program counter points here, and the page table points to the page table pointer points to the page table that is somewhere in memory in the OS area. Okay? But when we switch, we do context switching from this PCB to another PCB, which means from one process to another. We have to gather the stack pointer, the program counter, and the page table pointer from the CPU, right? Copy that back into the process control block, select the new process that is going to run. What is the program that selects the new process that is going to run? The scheduler, right? And then we get that PCB, copy the stack pointer from the PCB process control block into the CPU, the program counter into the program counter register in the CPU, and the page table pointer into the new register in the CPU that we call the page table pointer. So when we do context switching, we'll have to change from one program to another, and from one page table to another. Because the first program perhaps has 200 pages, but perhaps the second program has only 3, and they have different page tables. Are you following me so far? That's good. Okay, so that division that we were doing with the first example, where we have the program instruction, we divide it into pages and so forth. What we're saying is that this is the program once it's transformed into a process. So what we're going to page is the text or code area, the data area, the heap area, the stack area. This is what we're going to divide into pages, and these pages have to be loaded into memory. Because remember that when the program is run, it uses a stack. It points to the code, retrieve data. If you are working in a programming language that handles memory dynamically, you're going to use the heap. So if you see the book, what you're going to find is what the example that we did with the pages and instruction, they will use stack, data, text that they call it code, or heap. Okay? So start reading. Does anyone has the book here today? No? Okay, that's good because it's heavy. Okay, I think it's chapter 8, okay? Double check that. If you take a look to chapter 8 very briefly, then you will see how they are doing the explanation on paging with this version of the program, stack, text, and so forth. Okay. All right. Have a